Physical reality is continuous, flowing perfectly without interruption. But computational architecture is discrete, operating in strictly finite limits. Traditional quantum mechanics relies entirely on continuous math. To describe a particle's state, physicists use smooth wave functions managed through differential calculus. To bridge the gap between continuous physics and a machine's finite memory, we use a numerical grid. Locking the calculation to a specific number of locations translates continuous curves into individual coordinates, allowing us to process physical laws using discrete algebra. Solving quantum mechanics on a machine translates the continuous movement of calculus into the discrete logic of data. We will simulate the simplest confined system in quantum physics, the one-dimensional particle in a box. This diagram outlines the environment, an infinite potential well where energy is zero inside a box of length L, but infinite at the walls. Because the particle cannot exist beyond these infinite walls, the mathematical wave function must be exactly zero at the boundaries. Inside the box, the time-independent Schrödinger equation governs the system. To simplify our code, we set reduced Planck's constant and the particle's mass to 1. The equation's structure is straightforward. A kinetic energy operator acts upon the wave function to yield the total energy. We are looking for the stationary states of this system. That turns the physics challenge into a mathematical eigenvalue problem, where solving for the operator gives us the specific energy states. The immediate challenge in building this simulation is the kinetic energy operator. It requires calculating a continuous second derivative, which a computer cannot process directly. This comparison demonstrates the solution: spatial discretization. We divide the total length of the box into n distinct points, separated by a uniform spacing of delta x. To approximate the curvature of the wave function using only those discrete points, we apply the finite difference method. This method uses a 3-point stencil. It estimates the derivative by comparing a point to its left and right neighbors. The formula applies a negative weight of 2 on the center, balanced by positive weights of 1 on adjacent sides. That entire relationship is scaled inversely by the square of the distance between the discrete points. By applying this formula, complex continuous curvature is successfully reduced to a simple algebraic combination of 3 adjacent numbers. The 3-point stencil calculates the curvature at one single location. To model the whole box, we must apply it across every point in the numerical grid simultaneously. We hold these equations inside a tridiagonal Laplacian matrix. The stencil center point maps down the main diagonal, filled by -2 values. Neighboring point interactions fill the bands immediately above and below, populated by +1 values. The edges of the box are implicitly excluded from this matrix to strictly enforce our boundary condition that the wave function remains 0 at the walls. This specific geometric arrangement of numbers encodes the complete physical curvature of the confined space. We can now translate this mathematical framework into Python syntax. This code block demonstrates the setup. We define our physical constants, set the grid points n to 1000, and use NumPy to generate the spatial arrays. To construct the engine, we program the main and off diagonals independently using array functions, then combine them. Finally, we formalize the Hamiltonian matrix by scaling that Laplacian variable by our defined kinetic energy constants. The differential calculus problem no longer exists. It has been completely replaced by this newly built matrix. Now we run the core engine. We use a linear algebra solver to calculate the eigenvalues of our Hamiltonian. The solver outputs allowed energy states and structural wave functions, and we specifically isolate the lowest 3 states for observation. Numerical methods provide a direct path to the solutions of quantum mechanics, condensing the search for allowed energy states into a single algorithmic command. Did our discrete matrix accurately capture the true continuous reality of the particle? This table compares our numerical output against the theoretical expectations derived from the exact analytical energy formula. The calculated discrete values align closely with theoretical expectations, matching the exact analytical results to several decimal places. The matching numbers prove the validity of the finite difference algorithm. Any microscopic deviations deeper in the array are simply artifacts of the finite grid spacing. We visualize the results by plotting the specific eigenvalues extracted from the solver. This line plot shows the physical shapes of the first 3 wave functions. The physical constraints were respected. all three curves converge to zero at the exact boundaries of the box. Analyzing the wave shapes shows that an increasing number of internal nodes corresponds to sequentially higher energy quantum states. The process takes us from a purely theoretical constraint to a verifiable physical geometry. This flowchart tracks the complete pipeline, translating the continuous differential equation to a finite grid, mapping that grid into a tridiagonal matrix, and processing the arrays to extract the solved eigenfunctions. Discretizing space bridges the gap, allowing the standard operations of linear algebra to describe the continuous dynamics of quantum systems.